Okay, welcome to Chapter R, Section 6, Exponents, everyone's favorite topic, right? I know we've touched on this a few times, like in previous classes. So this one will be pretty quick. I just want to go over a bunch of exponent properties. Once again, most of this I'm sure you've already seen before. Most of this we've already talked about in class, but just want to do a quick review and make sure we're all on the same page. So first up here we have the definition of an exponent. All right, so this is a pretty standard definition, right? It's just exponents are just shortcuts for multiplication, right? A times A times A. Ooh, I gotta get a new point for my stylus. Keeps falling out. Times A times A, right? That would get really tough, really annoying to write over and over again. So we just came up with this handy shortcut. A to the fourth, right? That's how we say that. A to the fourth. Or a to the power of 4. But that's all exponent is. It's just a shorthand notation for something. I mean, there's more complex reasons for it as you get higher up in math. But for right now, for us, it's a shortcut to multiplication. Here's some of our exponent properties that we need to know. I'm sure you guys have seen this before. Anything to the 0th power, 57 to the 0 is equal to 1. Right, anything to the 0 is equal to 1. So it doesn't matter what you have. So even if you have x to the 0, doesn't matter what x is, the answer is still 1. So you don't have to worry about that. And then something else some people do get hung up on is negative exponents. Negative exponents doesn't really kind of mean what you might think they mean, being like negative numbers kind of being, going the opposite direction on the number line, things like that. A negative in front of an exponent means you just move it. If it's in the numerator, you move it to the denominator. If it's in the denominator, you move it to the numerator. So like the example they have there, a to the negative n is equivalent to 1 over a to the n. Right? So you see what we did there? Another way to write a to the n is a to the negative n over 1. Right? If we wanted to write this as a fraction, a to the negative n over 1, since we have a negative exponent, we would just move it to the denominator. And it will become a to the n. Just be really careful. It's super easy to put a negative sign there as well. You put it to the denominator, but then you still put it and you still make the exponent negative. I've definitely made that mistake before. You'll probably see me make it at some point, but it's just something to check on. But then I guess a lot of people can wrap their head around this. It's a relatively easy rule to just learn and memorize and use. Something people forget often is if you have an exponent in the denominator already. Let's say we have 3 over x to the negative 2, right? So if you have a negative exponent in the denominator, you can then move that to the numerator, right? So this would be equivalent to 3x squared. So I think that's where more people get hung up, is when you have a negative in the denominator already, that then moves it to the numerator. I don't really know why more people get hung up on that, because it's really just the same property. You're just, like I said, if it's in the denominator, numerator. If it's in the numerator, denominator. But I guess a negative exponent in the denominator can kind of freak some people out. So maybe that's why. But that's the rule does go both ways. So just keep that in mind. And then over here we just have your exponent properties, your basic ones that I think I think we've talked about pretty much all these previously in class. Especially 1 and 2. 3 is a good one. If you have, x squared to the 3rd power, like I said, I think I wrote this out before. You could write this out as x squared times x squared times x squared, and then that would be equivalent to x times x. At least the parentheses are just for clarity. X times x like that. But what you have, then you end up with x to the 6th. So what that means is when you have an exponent to an exponent, you multiply the two exponents together, right? I know I said this in a previous lecture as well. If you're ever having trouble wrapping your head around some of these exponent properties, just write it out. Literally write the problem out without exponents, and it'll become pretty clear what the answer should be, right? So like in this case, we had x squared to the 3rd. So I wrote x squared times x squared times x squared. That gets rid of the x squared to the 3rd part, right? Because there's 3 of them. And then inside each of those parentheses, the x squareds, I replace those with x times x because that's what x squared represents. And then what you have is you just have 6 x's all being multiplied together. So x to the 6th. Just be careful. Just don't write Don't write 6x. I'll freak out. If anybody writes 6x, I'll freak out. I'm just kidding. It's an easy mistake to make, but just, understand the difference between 6 to the x, x to the 6th and 6x, right? This x to the 6th is x times x times x times x times x times x, and 6x is 6 times x. Very, very different. Yeah, I think that's pretty much it. 4 and 5 are pretty straightforward. Just you can distribute exponents to parentheses. So if you have a times b to the x to the whatever, that exponent is applied to each one of those. And if same thing with a fraction, if you have a over b, that exponent's applied to both of those. One of the things to be careful with is, like, even we've been doing this all the time when we write quadratics, right? You'll see, like, 2x squared plus 3x minus 7. So this square is only on the x term, right? The 2 isn't squared. If they want the 2 to be squared, you'll see it written in parentheses. So you'd see 2x, the quantity squared. So just make sure you recognize the difference between these two forms of notation. I mean, I don't really need the 3x minus 7, but just for consistency, these are different, right? This is 2x squared plus 3x minus 7, and this is 2x, the quantity squared. So this would become, so if you have, like I said, I really don't know why I wrote the rest of that out, but 2x squared would then become 4x squared. Like, that would be how you could write that. And then, just recognizing the difference between the two is crucially important. That would be an easy mistake to make, and it would give you the wrong answer. So let's make sure we don't make that mistake. All right. Cool. Man, making these videos with no audience can be rough. It's just literally me sitting here in a room by myself talking to myself. I thrive on feedback, But okay, so let's apply some of the rules we just spoke about right up here. I'll even drag this down for us here so we can see it. Let's apply some of these rules to some problems here. So we have 7 to the 4th times 7 to the 6th. So that's going to be pretty straightforward. Rule number 1 here. So if we wanted to be super thorough and rewrite this, it would be like writing 7 to the 4th plus 6th, or 7 to the 10th. I have no idea what 7 to the 10th is. It's a large number, but that's how, since it's both the bases have to be the same. I probably should have mentioned that. You can see from the examples, but yeah, you have to have the same bases, right? The 7 has to be 7 and 7 in this case. In order to combine exponents, you have to have the same base. And when I say base, I mean the number that is being raised to an exponent. That would be the base. So in this case, our base is 7. So 7 to the 4th times 7 to the 6th becomes 7 to the 4 plus 6, or 7 to the 10. In our next example here, we have 9. So I can show you a little a trick with this one if you forget how the subtraction thing works, like what we just talked about. So we have 9, right? 9 to the 14 over 9 to the 6th, right? So if you just go up to property 2 over here, and you can just recognize, you can rewrite this. So they have the same base of 9, and then we're going to do 14 minus 6, right? And then that just becomes 9 to the 8th. I can show you, I keep saying a lot. It's kind of driving myself nuts. I hope it's not racking your brain like it is mine. I'll try to cut it out, I promise. I just paused and I was going to say but then I didn't. Another way to approach this, if you just don't memorize this rule, if you just understand your properties like we just talked about with the negative exponents, check this out. So we have 9 to the 14 over 9 to the 6th. What we just learned, right? Division and multiplication, well, not we just learned, but previously, division and multiplication are almost interchangeable. So let's rewrite this. Let's rewrite this to 9 to the 14 times 1 over 9 to the 6th, okay? Well, how does that help us? That doesn't help us. That looks even worse. What are we doing here? Let's take it a step further. So we recognize that making an exponent negative will move it from the numerator to the denominator, or from the denominator to the numerator. So once again, we can rewrite this like this. 9 to the 14th times 9 to the negative 6th. And now you have two numbers with the same base being multiplied with different exponents. So we know that would technically be property 1. where you add the exponents together. So you'd have 9 times the quantity 14 plus negative 6. And then obviously 14 plus negative 6 is just the same as 14 minus 6, and you end up with 9 to the 8th. If you're not impressed by this, I'm sorry. I find it cool. It's just like, I don't know, it's like a little math thing that I think is pretty interesting. I hope it helps your understanding of multiple properties here, but it is one of those things I've said. I have a terrible memory. I'm terrible at memorizing stuff. Like if I sat here and tried to memorize these properties, it would take me forever. I'd be really bad at it. If you understand the rules, like I said, don't break any math rules. If you understand the rules of math, you don't really have to memorize much. And I realize I'm coming from the perspective of, like I said, I have a terrible memory, so I don't want to memorize stuff. I want to learn. I do understand the flip side of that is some people are like, well, I'm really good at memorizing stuff, so I'm just going to memorize all this and not care about how it works. And that's a fair point. I do need to see things from your perspective, but if you're looking to succeed and progress and excel in mathematics, I would recommend trying to take a more critical thinking approach and comprehension of the basic building blocks rather than just memorizing a bunch of rules and saying, I know all these rules, and then not being quite as good at applying them. So just my 2 cents. Like I said, I see things from my point of view, but I want to try to, be able to give you guys a good reason, even if you don't necessarily think like me. This next one with the R, I'm just going to skip that. It would just be the same thing. It would just be R to the 9 minus 17. Well, I'll just write it out real quick. R to the 9. Oh, I don't know where parentheses go anymore. 9 minus 17. So then you'd end up with R to the negative 8, and then that could be rewritten as 1 over R to the 8. I'd say the argument between this and this is there's not necessarily a better way to write it. Honestly, I'd probably prefer the negative exponent. It's less, I think it's less pencil strokes. It's less to write. In terms of the MyLabs, just keep in mind when you're answering questions, if it says write your answer using only positive exponents, you would have to write it like the solution on the right, the 1 over R to the 8th. So you guys are all super smart, so you know that. Taking a look at this next one down here, we got 2m to the 3rd quantity to the 4th. So let's be super thorough and write this out. So this would be 2 to the 4th times m to the 3rd to the 4th. So then 2 to the 4th is what? 2 times 2 is 4, 8, 16? 16, that's just 2 to the 4th, and then m to the 3rd to the 4th would be m, well, let's keep being consistent, writing out every step, times 3, m to the 3 times 4, or 16 m to the 12th. Ta-da! And E would be the exact same, there's no trick there. F is just recognizing the rules again. X squared y to the 3rd quantity to the 6th would be x squared to the 6th over y to the 3rd to the 6th, and then you just distribute. That's not really distributing, it's exponent to an exponent, but you'd have x to the 12th over y to the 18. Oh, let's look at this next one's getting crazy on us. Look at this. A to the negative 3rd, b to the 5th, a to the 4th, b to the negative 7th. We're getting crazy now, am I right? One thing I will say, when you're doing a lot of simplification of rationals with exponents, like something like, like g here, there's a lot of different ways to approach it. Like there's many different ways you could do this you could write this problem out. It's really up to you. Since you can, a popular way of doing it, I'll say, or a common way of doing it, is what people will do first is try to remove all the negative exponents. So like a good first step would be to move the a to the negative 3rd to the denominator and make it a to the 3rd, and move the b to the negative 7th to the numerator and make it b to the 7th. So you'd have something like b to the 5th times b to the 7th over a to the 4th times a to the 3rd. So that's a super common way to approach it. If you wanted to, like, another one for this, since you have the two bases with the exponents, like, you could technically move everything to the numerator, simplify it, and then see what happens. In this case, this first method I took is probably going to be the best, because you're going to have a b in the numerator and a in the denominator, so it's going to look pretty good. But there's really, as I say, as long as you don't break any math rules, there's a lot of routes you could go with this, but this would just wrap up as b to the 12th over a to the 7th, and that would be it for that. These more quote unquote complex rational exponent expressions, just practice. Just go out and practice. They might look intimidating in the beginning, but I promise, if you put the time in, you can master these without a huge level of effort. But you gotta put the time in. You gotta get used to working with them. A big thing I recommend for everyone is kind of try to find your own workflows. Like, find what works for you. Like, maybe you like making all the exponents positive first. Maybe you like grouping the bases into the same area. Like I said, there's lots of ways to do it. Try to find a way that works best for you, and then kind of just hone that skill. Use that technique. If you need to make changes, try to figure out where you're getting jammed up. Like, if you're getting stuck at the same part of a problem every time, try to recognize that and say, okay, I get to this part, I get to b times b to the 5th times b to the 7th over a to the 4th times a to the 3rd, and then I always mess up the next step, right? One of the best ways to get better at not making errors, that's a weird way to say it, to get cleaner with your work, is recognizing where you make the errors most of the time. A lot of times you'll see patterns. Like, people will make mistakes doing, people will be really good at certain aspects of algebra and be poor at other ones. So if you just think like, oh, I'm bad at these kind of problems, well, maybe you're only bad at one specific skill you need at a certain point in the problem. And if you can recognize that, you can practice that one little skill rather than trying to practice a 5-minute problem when you really only need help on one step that might take 30 seconds. So doing one problem gives you about 30 seconds of improvement. If you recognize that that's the skill you need help with, you can study that skill and do, 5 minutes and 30 seconds. You could practice 10 of those problems in the same amount of time before you were only doing one. So you're using your time so much more efficiently and getting more out of it. I guess that's kind of the definition of efficiency. But so just recognizing your deficiencies and striving to improve on those techniques can really, really help you in the long run. I mean, and in the short term as well, really. All right, let's take a look at a couple more of these. Oh man, I'm gonna have to bust out the calculator for some of these. So I don't know if it actually talked about. I might have missed this part, but fractional exponents, right? Fractional exponents, everybody's favorite. So x, and then I will write this like this. I will write p over I. This is how I remember it. Power over index. So a fractional exponent is equivalent to the index of the root and x to the p, right? Power and index. So a power is your exponent. The index is it when you have a square root, a cube root, a quad root, a fifth root, blah, 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 blah. That's called the index of the root. So if you don't see anything there, right, the common one is just that. That's a square root. There's a pretend 2 there. You just don't know it. Or we just don't have to write it. Square root is the basic one. But obviously there's also, cube roots and seventh roots. Seventh root. That sounds kind of tough. But when you have a fractional exponent like this, I guess this was probably in the book. I probably just forgot to grab it. But power over index. That's how I remember it. Power over index. And you can go the other way as well. You can have a radical here and then change it to an exponent. But in most cases, you're going to be given a term with an exponent, a fractional exponent, and you're going to use your radicals to solve said problem. Like what we have here in A through G here. I didn't even realize there's actually a 1 to the 7th or a 128 to the 7th down there. That's got to be 2, right? I think so. We'll get there. One of the good things about this, I actually should kind of write this out a little. I want to write one more here. If you go out here, one cool thing about exponents and radicals, you can do them in either order. So this could also be written as, the ith root of x quantity to the p. So that might not seem like much, but it's very helpful in solving some of these problems, which we'll take a look at. So what we're really saying here is, you can either raise x to the power first, then take the radical, or you can take the radical and then raise x to the power. I guess these are all to the 1, so all the powers on these are 1. This is really just radical practice. But we can take a look here. So 121 to the 1/2 can be rewritten as, it's just the square root of 121. That's all it is, because the power is 1, so we don't need to write that. The index is 2, we don't need to write that. So the square root of 121 is just 12. No, the square root of 121 is 11. I'm really bad at math, guys. Cut me some slack. The square root of 121 is 11. So same. I mean, this is just calculator work, really. Like I said, I don't know what these. I want to say 625 is to the 4th. It's to the 1/4 is 5. 625 to the 1/4 can be written as the quad or 4th root of 625. It's got to be 5, right? I think so. 5 times 5 is 25 times 5 is 120. Yeah, it's got to be 5. 256 to the 1, also to the 1/4, gives you the quad root of 256. I'm guessing, is it 8? Is that 8? No, how can it can't be 8? It's got to be less. Is it 4? It should be probably 4. Yeah, it's got to be, because it's got to be less than 5, because 625 is less than. Yeah, 4 times 4 is 16, times 4 is 60 something, times 4. Yeah, okay. Keep on keeping on here. So 27 to the 1/3. I think you guys get the idea at this stage. The cube root of 27. I do actually know this one is 3. It's got to be 2. I don't actually know, but it's got to be, right? Somebody watching at home, do the math real quick. The seventh root of 128. It's got to be 2. It's just got to be. There's nothing else it could be. Can't be. So that's just a quick approach. Once again, I would just highly recommend just doing a lot of practice. I know I kind of talked about the whole power over index thing. These ones all had just the 1 as the power. But like I said, you can do them in either order, and you'll see instances like. Now I'm gonna try to come up with one off the top of my head. Okay, like if you had 25 to the 5/2, something like that, right? So we could rewrite this as the square root. It's the square root. So the square root of 25 to the 5th, right? So if we have a calculator handy or whatever, yeah, we could just plug 25 to the 5th into our calculators and solve that, and yeah, we'd get a number. Then we'd take the square root of it, and we'd be done. But what you could rewrite this as the quantity of 25. The quantity of the square root of 25 to the 5th, and then you can the radical 25, square root of 25. We can do, right? We know that's 5, and then you have 5 to the 5th, right? And then that's, I don't know what that is. But it is like, that's what I was just saying. Like if you have an instance where you can't do the square root, or you can't do the exponent off the top of your head, if you have the ability to do the radical first, you can. Or if you wanted to do the power first, you can do either one first. Is all I'm trying to stress. It's a little small. What's this say here? No. Yeah, so it's just using another property. This isn't really doing anything. It's kind of just using our rules we talked about earlier to just kind of break up these exponents here. So if you have 2 exponents being multiplied or divided together, you can do an exponent to an exponent. So that's all we have here with this a, right? M over n. Is that what we have? Yeah. Oh yeah. Power over index stuff. So I like my way better, but I mean, I get what they're doing here, but it's just saying, so you'd have a, right, to the 1 over n times m, and that's That's all it is. There's nothing really to it. They put the extra parentheses on there, but I like you guys see, I love parentheses. I really don't see a need for parentheses there because you can. It doesn't have to be a to the 1 over m or 1 over n quantity m. You can do the power of m first if you wanted to. Like I said, it's just what I just discussed previously. But either way, I like my reasoning better, but you can see they got their own little deal here. So let's take a look at some fractional exponents and simplify some stuff. So, we got y to the 1/3 times y to the 5/3 over y to the 3rd. Whoa. Once again, not really a correct order to do these. It's as long as you don't break any math rules. With this one, there is a pretty straight path to the solution. I would definitely combine the y's in the numerator. So the numerator is going to become y to the 1/3 plus 5/3. Look at that. They gave us the same denominator. That's so nice of them. Over y to the 3rd. So then the numerator, like I said, we have the same denominator. So it's just some quick fractional arithmetic there, which we're so good at. So we'd end up with y to the 6/3 over y to the 3rd. And then just like with regular fractions, with fractional exponents, you can reduce these fractions. So this would just become y squared over y to the 3rd. So the 2 came from 6 over 3, right? 6 over 3 is just equal to 2. Look at that. And then finally, whenever you're dealing with these problems, simplifying rationals, or just simplifying anything with exponents, in general, you're going to only want to have one of every base in your solution, right? So we still have 2 y's here. Well, a y in the numerator and a y in the denominator. We're going to want to combine them into just one term. So in this case, this will become y to the negative 1. Because we have 2 y's in the numerator and 3 y's in the denominator. If you don't believe me, look at this. Y times y is y squared. Why am I doing this, right? that was probably my worst joke yet. I'm gonna save that one as the dumbest thing I've said so far, but you guys be the judge and we'll take it from here. You guys can start an ongoing discussion post about my most terrible thing. That terrible is a bit harsh. Anyway, y squared in the numerator, y divided by y is 1, y divided by y is 1, and we're just left with 1 over y, which is equal to y to the negative 1st. There's 4 more. There's 3 more problems. I thought we were almost done. So the next problem here is we have a little bit of distributing with fractional exponents. Look at us go. We're hitting the big leagues now. So we're going to distribute this m to the 2/3 to both of these 2 terms here. So if we do that, we'd have m, and then we'll have, since we're multiplying, right, we'd have 2/3 plus 7/3 over here. And then here we'd have 2, and then same thing, m to the 1/3, 1/3 plus 2/3. There we go. So that's really that, and then just do some math, right? 2/3 plus 7/3, so you get m to the 9/3 plus 2m to the 3/3. Look at that. I said again. I'm trying to stop, but I can't do it, guys. M to the 3rd plus 2m. Yeah, and that's it. Nothing. Can't combine those terms. Right? We got an m to the 3rd and a 2m. Can't do it. This does not equal 2m to the 4th. Don't you do it? Don't do it. I'm looking right at you. Don't do it. Don't you do that. That's breaking math rules, right? Yeah. So just moving right along here. Let's do this thing. Look at this one. This one's getting exciting, right? So we got m to the 7th, n to the negative square, n to the negative 2 over m to the negative blah, 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 blah. So what I'm going to do with this, I'm going to take the approach of I'm going to try to simplify what's in the parentheses first. Once again, you could absolutely distribute this 1/4. It's not really distributing. You can absolutely... I almost said distribute again. You can absolutely take this 1/4 and raise each of these terms to 1/4 if you want. You could, and then combine the exponents. You absolutely could do that. Totally viable. In this case, doesn't look super helpful to me, but maybe that's how you want to roll. I'm going to get rid of the negative exponents and combine all my bases first. That's what I'm going to do. So I'm going to rewrite this as m to the 7th, m to the 5th, n squared, and then this is still all to the 1/4. Now I'll combine my bases, or combine like terms, m to the 12th over n squared, and then once again I wrote n squared. I said n squared, but I wrote n to the 4th. Then finally this is all to the 1/4, so then m to the 12th to the 1/4 over n to the 4th times the 1/4. So this is nice. We don't actually have to do any of the radical stuff because this all just reduces. So this would just become m to the 3rd over n to the 1st. Ta-da! You guys know, I know you're sick of hearing it from me, but practice is how you do these problems. You gotta just practice. You can watch me do it all day. I'm real good at it, I know, and it's super exciting to watch me do these problems, but trust me, guys, it's so much more fun if you do it yourself. Alrighty. So we're going to change gears a little bit. I didn't actually write the problem down, but we're going to change gears. So here we're actually we're going to look into factoring terms with exponents. So this is a good skill to have. This does come up in calculus, I will say. There's integration problems where you'll need to factor even binomials with negative exponents or exponents. This one doesn't have negative exponents, but you'll factor like terms that are radical terms. Like you might factor like an x plus 2 from a polynomial. So it is a skill that's not used a ton, but when it does come up, I know it does trip people up. So it's like I said, it's not used super often, but it is important to understand how it works. So like for this problem, looking at this, we have a 4 and a 3, so we can't really factor anything out of the constants. But then we have an m to the 1/2 and an m to the 3/2. So we can factor out an m to the 1/2. And then this first term is just going to become 4 because m to the 1/2 divided by m to the 1/2 is just 1. So then what we have here in the next term, let's write this out first, because what we're actually doing is we have m to the 3/2, and what we're doing is we're dividing by, not n, m to the 1/2. That's right, that's what factoring is, because if you distributed this, the m just the 1/2 would just divide out and you'd be good. So if you want to get into the habit of how this works, you can start by writing it out this way. Then nothing's really going to change with the rest of it. But then if we want to write it as a subtraction problem, right, it would be m to the 3, not a subtraction problem, but if we want to subtract the exponents, right, because the m to the 1/2 is in the denominator, so you can rewrite this as m to the 3/2 minus, to the quantity 3/2 minus 1/2, and then finally m to the 1/2, 4 plus 3, and then what's that? What do we have? 3/2. So, just m to the 1st. Look at that. Oh yeah, it was 1/2 and then 3/2. Yeah. Yeah. And that would be your final solution for this problem, just like that. So I think that's the last thing I want. Yeah. So that's a recap of exponents. Like I've said it twice just in this 30-minute video. Practice, and then practice some more. Just a rough ballpark. If you do, say 10,000 of these problems, you'll be pretty good at it. That's kind of a joke, but kind of not. If you do 10,000 of these problems, you will be good at it. I don't know who has the time. How long would it take you to do 10,000 math problems? I guess it would, obviously you'd have to figure out what the average time it takes you to do a problem, and then just multiply that by 10,000. It's not a super tough calc, but either way, yeah, give it a shot. Let me know what you think. Tell me who can get to 10,000 first. Start your engines. Start counting. But seriously, get into the homework. Ask me any questions you have. I will be happy to elaborate on any of these problems. Break it out step by step even more if necessary. But get after the homework. Get on the discussion board in Canvas, and just keep on practicing, and we'll keep getting better. All right, thanks, guys.